In this video, we're going to go over the Bernstein-Vazirani problem, which is a somewhat artificial problem proposed by Ethan Bernstein and Umesh Vazirani, where we can see a quantum speedup that's pretty dramatic. So it somewhat resembles Deutsch's problem, which we went over in the last video, but the speedup here is wider, so the quantum advantage is even more clear here. And again, we're working with this oracle model of computation. So we're given access to some unitary, which is going to execute f of x for us. And this f of x is a Boolean function that maps a binary string of length n to 0 or 1. And the promise is that it's going to take this sort of scalar product, this modulo 2 scalar product between some hidden bit string a and your function input x. And what that looks like is you take each individual bit of a and x, and you multiply them together, and then you XOR the result. So this doesn't denote normal multiplication. It's this binary sort of scalar product that we have, and that's why it only returns 0 or 1. So the goal here is, how many invocations of f do we need to determine our hidden bit string a? So first, let's think about this classically. How do you even obtain some information about a? So we have n different bits that make up this bit string. So it seems like we're going to need at least n calls to f of x, and that turns out to be true in the classical case. So the way you'd do it is you'd prepare some x that's just 1 followed by a bunch of zeros, n zeros, or n minus 1 zeros, and then you plug in your f of x with this input, and this will give you the first bit of a. If instead that you prepared some random input with x, you'd lose information about each individual bits. So this is sort of the way you'd go about it classically. And then we could also prepare another x that'll give us the second bit, and so on. So of course you're going to need n calls to this function if you're working on a classical computer. Now, what about the quantum case? Well, I've written the circuit, or I've drawn the circuit up here in the upper right. And as you can see, it resembles pretty much exactly our circuit for Deutsch's algorithm, except our input is a little larger. We have n bits instead of just 1. But we're doing the same sort of trick here by putting our output register into this minus state. So let's just trace the evolution of our input register throughout this circuit and see what happens. So we start out in this 0 state, and the first thing we do is a Hadamard on all of these. And this is just going to prepare an equally weighted superposition from 0 to 2 to the n minus 1. And we have this normalization out here. Right? And implicitly there is this output register here, but I'm not going to need to write that. And now the next step is we apply our unitary, which is this sort of controlled f I have written in the circuit. And the result of this, if we can recall from the previous video, u of f on some generic input x, while our output register is in this minus state, is negative 1 to the power of f of x, and then minus. So we sort of lift this f of x function to determine the sign of each individual term in this superposition. And what we're going to get here is the same thing, but now we have this relative sign depending on the function value of x. So now I want to apply a Hadamard here. I want to apply the final Hadamard and see how this state is going to evolve. But in order to do that, since this Hadamard is going to end up hitting our x state, and for each term in the superposition, we want a better understanding of what happens here. because we haven't really discussed the more general case where we have n qubits. No, so we know if we have 1 qubit, for example, and we apply a Hadamard to it, I can write this state in this sort of condensed notation where we have this phase factor here, this sign that depends on the value of x. And we can quickly check that this gives us the right values for 0 and 1, which are the only two possible 1-bit values. So if it's 0, then this -1 being raised to the power of 0 is just 1, so we get the plus state. And if it's 1, we have this minus sign, giving us the minus state, which is correct. But this can also be written as a sum where we go from y is equal to 0 to y equal to 1. And then we have a phase factor that also depends on the current bit of y, or the current term in the superposition. Because we had -1 to the power of x over here, but we didn't have it over here, and this is how we sort of encode that information. And these two things, again, are equivalent. And this is nice because it gives us a path forward to actually thinking about what this thing is going to look like. And the way we do that is we just say, okay, so for each bit, we know that the result of the Hadamard on that bit is going to be this state. So the total action of this Hadamard on all n bits is a tensor product of these sort of sums. So firstly, I'm just going to multiply out all the normalization constants that we're going to get for each n bits. And this is going to leave us with the 1 over the square root of 2 to the n. And then we have a sum for each individual bit. So we'll start with the most significant bit. Goes from 0 to 1. And this is going to continue to the least significant bit. And then we have, within each of these sums, but I can just pull it out to the rightmost sum, we have these phase factors that depend on the current bit of y as well as the initial value of x. But we have to refer to each bit individually. So we have the n-1th bit of x and y multiplied together. And the same thing all the way down to the least significant bit. And then we have this tensor product, which just ends up being our current binary string that we're on. And if we're cycling through each binary value for each bit of y, this is actually just the same thing as a sum from the total y that represents the whole bit string from y equal to 0 to 2 to the n-1. And since we're multiplying these exponents, these -1 raised to these powers, we can just add what's actually in the exponents. So we get -1, and then we get this sum here where we go from I is equal to 0 to n-1, and in the sum we're multiplying the ith bit of x and y. And this, of course, is just the same thing as this sum where we have this scalar product between x and y, this modulo 2 scalar product. So now that we know this, and let's just be more clear, this is the action of n Hadamards on some generic state x with n qubits. So we can use this now and start looking at how this state is going to evolve. I'm going to drag it over here. So when we apply this Hadamard, we're going to get two sums now. So we have our first normalization constant, and then we need to include the second one for the second sum we're going to get for all the y values. So we have this first sum, and now we also have this second one. That goes from 0 to 2 to the n minus 1. And we have two sort of interfering phase factors here. And now we're cycling through all these values of y. So let me condense this and rearrange it a little bit. We can multiply these two normalization factors. We have 1 over 2 to the n. And then I'm going to switch out. I'm going to put this y sum to the left so we can just zoom in on this x sum and see what happens as we cycle through the values of x. Because we're going to get some pretty interesting interference effect. And now I'm just adding these two things because we're multiplying two exponentials. And now we can substitute the value of f of x. What is it actually computing? Well, it's computing the same modulo 2 inner product or scalar product between a and x. So we can write that. And it's a little annoying having to write these sums every time, but it's okay. So we have -1 to the power of a product with x plus y dot x, because x dot y and y dot x is the same thing here. And the reason I wrote it this way is because now we can use the distributive property for x, and we can pull out x here. And we can get this state where for each value of x and each value of y, we have this XOR between a and y dot x. And now we can start to actually examine the different scenarios. So it turns out there's only two types of scenarios we have to consider here. The first one is when y is equal to a. So this corresponds to a single term in the superposition where y is actually equivalent to our hidden bit string, which will appear in our superposition if we do an equally weighted state of all the different values from 0 to 2 to the n minus 1. There will be one value where y is equal to a. And in that case, we have that a XOR y, which is just a XORed with itself, is going to be 0. So as this sum cycles to every value of x, we just have -1 to the power of 0 dot x, which is just -1 to the power of 0, which is just 1. So we don't get any flipping of the phase factors. And what ends up happening is we sum 2 to the n terms where each term has a amplitude of 1 over 2 to the n. So 1 over 2 to the n times 2 to the n is just 1. And this is actually already enough to tell us that the state that we're going to be left with is just y is equal to a, and we'll be complete. But to drill it in even further, let's examine what happens when y is not equal to a. When y is not equal to a XORed with y is just some string x, some bit string x that we know is not all 0. So it has some 1s littered throughout this bit string. And what happens is as we cycle through the values of x, and it's not too difficult to see that we're going to get as many -1s as we will get +1s. So the same number of times that we're going to have s dot x equal to 1, where this is the modulo 2 inner product, or we're going to have just as many times that s dot x is equal to 0. And what ends up happening is all the times that it's 1 cancels out all the times that it's 0 because of this flipping of the phase factor. So what happens when y is not equal to a is that the resulting amplitude is 0. So the only state that we could possibly measure in the input register after running the circuit is well, and I'll just go back to x because it's our input, is x is equal to a. So we don't even need to look at the output register. We've sort of just thrown a into there. And this was from one call, just one call of f of x, or a unitary that implements f of x. So we go from a sort of linear time classical algorithm where we would need to call this n times to a single call. And that's pretty amazing. So yeah, thank you.